Hello, welcome to our video. In this work, we introduce a gradient-based estimation method that accelerates task affinity computation for building scalable multitask learning systems. Multitask learning is a fundamental problem with a wide range of applications. One example is training graph neural networks to perform multi-label predictions on large networks. Another example is fine-tuning language models to follow instructions across NLP tasks with specially designed prompts. In multitask learning, tasks can influence each other both positively and negatively. The key concept for modeling these relationships is task affinity. For instance, pairwise task affinity is computed by evaluating the model loss trained on each pair of tasks. Higher-order task affinity is computed by training the model on subsets of more than two tasks. The main challenge is that the process requires training numerous multitask models on different task combinations, which becomes expensive as the number of tasks increases. Can we circumvent the cost of repeatedly training to estimate task affinity? The technical insight is the linearization property of neural networks. We start by pre-training the model on all tasks to obtain a meta-initialization. Since underlying tasks share structural similarities, the initialization can quickly adapt to subsets of tasks, and the adapted model often stays close to the initialization. Therefore, the adaptation procedure behaves like linear models locally. That means that we can approximate the task loss for a model trained on a combination of tasks by using a gradient-based Taylor's expansion centered at the meta-initialization. Interestingly, the approximation error for the fine-tuned model output is less than 3.5% across three distinct scenarios. With the linearization property, we design a gradient-based estimation algorithm to estimate task affinity. First, we collect gradients of every training sample at the meta-initialization. Then, we estimate the fine-tuned model parameters for subsets of tasks by applying Taylor's expansion in the task loss. This corresponds to solving logistic regression and mapping the gradients as feature vectors to the task labels. Therefore, we trade the cost of full model training by solving logistic regression. We call this algorithm the GradTIE algorithm. To evaluate the method, we consider three types of widely used neural networks, including graph neural networks, ResNet, and the T5 model. We use 8 datasets and estimate both pairwise and higher-order task affinity scores. We show that GradTIE can approximate true task affinity with less than 6% error, while using only 3% computation of full model training. Further, our method can scale to a dataset of 500 tasks using less than 113 hours, when full model training is not feasible. On top of GradTIE, we design a task grouping algorithm that clusters tasks into subsets and trains multitask models in groups, named GradTag. Our GradTag algorithm gives the best trade-off between computation and performance among existing multitask learning methods. Thanks for watching. Make sure to check our paper and open source release.